Yeah, so thanks very much, Antoine. I'm very pleased to be here for this nice symposium. So I'll be telling you about work that my group has been involved in for, well, close to 10 years now, actually. And we've been studying a class of 4 and 5D double perovskites. Actually, we initially started to study these because of our interest in geometrical frustration, but in fact, the arc of the project has changed somewhat over the last decade. Um, at any rate, so this work was really a collaboration between my group at McMaster University and Aaron Paramakanti's group at University of Toronto. So that's who most of the collaborators are here. And of course, very important collaborations with the large-scale facilities at which we do our neutron and X-ray scattering measurements. Um, Right. So you probably know that perovskites are a very large class of materials, and double perovskites are also a very large class of materials. So the perovskite structure is shown here in the bottom left panel, and perovskites have a composition of AbO3, and they're basically a network, a three-dimensional network of corner-sharing transition metal octahedra with a cation in the middle. So nature really likes this structure for oxides, and very similarly, the nature also likes the double perovskite structure, which is shown in the top right. And here, the idea is that you simply alternate every second transition metal oxygen 6 octahedron with a different transition metal. And if you can get the transition metals to order, as they often do, um, then you can form the structure that you see here in the top corner, where every second transition metal octahedron has either a B or a B prime site. So it's if you like, it's a sodium chloride type of order. So what I like about this particular structure is that it's very flexible, that there are many different 4D and 5D ions that you can put into the octahedra. Actually, the cartoon at the upper left or the upper right, sorry, is for a cubic double perovskite. What is much more common in nature is something with symmetry lower than cubic, tetragonal, monoclinic, and such. And so then the octahedra are tilted, as you see in the middle panel here. But actually, our selection criteria to decide which double perovskites to study, we've aimed for cubic double perovskites. So that's a small subset of all double perovskites. And the initial choice for that was that the sublattice associated with either one of the B or B prime sites in the double perovskite structure form an FCC lattice if the double perovskite is cubic. And the FCC lattice, as you know, is a network of edge-sharing tetrahedra, and so this initially motivated our interest in these materials. So as I mentioned, they're very flexible materials. I hope you all recognize this as the periodic table. Um, and um, and so the highlighted elements are the ones that we've incorporated into double perovskites thus far. Actually, you can see that for this sort of family of barium-based double perovskites, which are a lot of the ones that we've studied because there are many cubic examples. Um, the barium, of course, is in a 2 plus oxidation state, the oxygen in a 2 minus. So that means that the total oxidation state of the B and B prime sites, which are in this case magnesium and rhenium. Can you see where I'm pointing, by the way, in my slides?
Yes.
Uh, you see my pointer? Yeah, good. Okay.
Yeah.
So the total oxidation has to add up to +8, and so what we are generally aiming for is a B site that has only filled or empty orbitals, and a B prime site that has partially filled orbitals. And in all the cases I'll talk about, they're either partially filled 4D or 5D orbitals. So you can see if you have a B site that is like an alkali, a metal ion, then you're going to combine, say lithium with rhenium or osmium 7 plus, because they have to add up to 8. And so magnesium will be osmium 6 plus, and yttrium would be osmium 5 plus. So there's a lot of flexibility to how you can build up these structures, and there are many of them. And in particular, you can look at a class of materials where basically you can put, say, ruthenium and osmium into the same double perovskite structure, and you can at least think to yourself that what you're doing is you're looking at the same physics while tuning the spin orbit coupling, which of course increases as you go down the periodic table. So this is the standard picture for the single ion physics associated with 4D and 5D systems, and 3D for that matter. And so the idea, of course, we were talking about d orbitals. So we've got L equals 2. And in the absence of any perturbation, they're fivefold degenerate. But the crystal field associated with the octahedral environment will split this up into a T2G triplet and an EG excited state. And so for the most part, we're going to forget about the EG excited state in the work that I'm going to show, and then apply spin orbit coupling, which would then take the 6 levels associated with the T2G orbitals and the spin degree of freedom, and break that up into a low-lying quartet, which is an effective the J equals 3/2, and an excited J equals a half doublet. So that's our standard sort of starting point. And actually, in this talk, I'm gonna talk about our experimental results on classes of D3, D2, and then finally D1 double perovskites. I'm going to start with D3, which are in some ways, well, in almost every way, the simplest to understand, and that's because with 3 electrons in the d orbitals, you can actually take a step back here, and provided that the Hund's rule or the Hund's energy is sufficiently strong, the 3 electrons will half fill the T2G shell, and you'll end up with an orbital singlet and a big dipole magnetic moment of 3 Bohr magnetons. And actually, what you would expect would be very conventional physics, where there'd be some Heisenberg type interaction, and it would order into a simple structure and give you spin waves that have no gap, because it's a Heisenberg type interaction, at least to the extent that you don't mix in the upper level EG. Okay, so if you continue down to this second stage, then you can see that would actually give you a J equals 3/2 degree of freedom. The plus and minus a half would cancel, but nonetheless, our expectations are a very simple system, and that's largely what we found, actually. So we've done measurements on a variety of these systems. But I'm going to show you just a subset of the data. So this is the data for barium-2, yttrium, osmium 06. So that's 5D3 associated with the osmium. And we did different types of neutron scattering experiments. In the top panel on the right, you can see neutron Bragg peaks in the elastic scattering that develop below about 70 Kelvin. What I'm showing you in the bottom panel on the right is the order parameter associated with this. Looks like a very conventional second order phase transition. And one can look at the magnetic Bragg intensities and try to fit to an ordered structure. Actually, the ordered structure that we fit to was more or less the simplest one that we could come up with. And the purpose of doing this was really to estimate the ordered moment associated with this structure. It wasn't necessarily to solve the magnetic structure because we didn't have that much information, right? There's only a few Bragg peaks that are observable. But nonetheless, we modeled our data, based on this single K antiferromagnetic structure, which means that the moments are arranged in planes perpendicular to a particular axis. So say the c-axis, although there is no c-axis if these materials are really cubic. And so that's a good reason why this likely isn't the real magnetic structure of this material. But nonetheless, this was sort of our starting point, and we could refine our data and pull out an ordered moment of about 1.6 Bohr magnetons, which is roughly half of what we would have expected for the spins of 3 electrons, which is 3 Bohr magnetons. Then the surprise was really in the inelastic scattering, which I'm showing you now here on this plot, because as I mentioned, as an orbital singlet, we were really expecting little or no anisotropy. But in fact, so this is the inelastic spectrum on the bottom panels. So this is a color contour map on the left, and then slices through that data on the right. And you can see pretty clearly that there's easy to observe inelastic scattering, but it's gapped, at least at low temperatures. And the gap is actually pretty big. It's at 17 MeV. And so this was definitely unexpected. And we really didn't know what to do with this so much. So what we often do is just try to expand the data set that we have and look around at systems that are nearby. And so we also looked at the ruthenate version of this crystal. So this would be barium-2 yttrium ruthenium O6 instead of osmium O6. So this is now a 4D3 system. So naively, at least, you'd expect all the physics to be the same, but for the spin-orbit coupling to be weaker. And indeed, we measure phenomenology, which is essentially the same. But the gap is about a third the size as it is in osmium, which is consistent with our expectation that the gap somehow arises from spin-orbit coupling. But it wasn't clear how. And so this paper that we wrote, which I'll give you the reference for later, sort of concludes without a conclusion. It just points out that there's an oddity present. But then Leonid, the second speaker, and I'm pretty sure he's going to at least mention this in his talk. So he came out with this work about a year ago, which sort of beautifully explains almost everything that we see. And it's really first principles treatment of the microscopic Hamiltonian that's relevant for this system. And the bottom line, I won't go into any more detail, but the bottom line is that there are both dipoles and octopoles occupying the osmium sites, and the dipoles actually order into this 2K structure. So it's it's a similarly simple Neel state, but it's not a single wave vector Neel state. It's a 2 wave vector Neel state. And the gap is generated by the coupling between the dipolar degrees of freedom and the octopolar degrees of freedom. And actually, with this determination of the Hamiltonian and some manipulation of the terms, all of the features that we observe basically could be reproduced, including the ratio of the gaps. So that had actually kind of a happy outcome to it. It didn't look like it was going to be happy for a while, but it ended up being happy. So I'll now go to the 5D2 systems, which are definitely more exotic. So we have the same standard picture for the 4D and 5D systems, but now we've got 2 electrons. And so now, of course, we end up with, the JZ equals minus and plus a half don't cancel anymore. And so you end up with a J equals 2 degree of freedom. And again, a 5-fold degeneracy in the absence of any other perturbations. And then for this system, or for this problem rather, we could synthesize this trio of 5D2 systems. They're again based on osmium, but instead of having yttrium 3 plus as the B site, we've got either magnesium or zinc or calcium 2 plus as the B site. So that leaves us with a 5D2 state for the osmium. And actually, so this is a series of compounds which we started to study, 10 years ago. And I'm just showing you here the relatively low temperature thermodynamics and also some zero field MgOsO measurements on powder samples. Actually, all the data that I'm going to show you today is on powder samples. Anyway, the data in the lower left, which shows identical heat capacity measurements on the osmate system, the 5D2 magnesium osmate, and magnesium tungstate. And the tungstate actually has no 5D electrons, so it's acting like an orbital blank or a magnetic blank, if you like, and but the lattice contributions to the heat capacity should be very similar. And at any rate, we see that there's an anomaly at about 50 Kelvin. And the fact that we've got this blank sample means that we can subtract the two and isolate the orbital or magnetic heat capacity and determine the entropy that's recovered up to about twice this transition temperature, which I'm going to call T star, but we initially called Tn. And we initially called it Tn because we thought it was another Neel transition. And the reason we thought it was another Neel transition is that the MgOsO measurements that were carried out, definitely saw the presence of time reversal symmetry breaking or internal fields, in the system that developed below 50 Kelvin. And you can see that in the top left as the appearance of these oscillations below about 20 Kelvin. So at first, this looked very much like a traditional antiferromagnet. And as I said, this entropy release that we determined, we've measured it for all three of these systems, and to within 10 or 20%, the entropy release to twice T star is roughly consistent with R log 2 and not with R log 5. So if nothing else, it's very clear that there's some breaking of this fivefold degeneracy, and at least up to 80 Kelvin or so, we're left with the relevant degree of freedom being some pseudo-spin a half degree of freedom. That's two of the five states that have been pulled down due to this perturbation, and it's the same in all three of these materials. Okay, so again, so my main experimental technique, apart from making materials, is doing neutron scattering. So this is what I will always go to in any project that I'm involved in. And so this is what the inelastic scattering looks like from one of these three materials. And the one that I'm showing you is barium zinc osmate, where that thermodynamic transition is at about 30 Kelvin. And on the left-hand side of this slide, I'm showing you a color contour map of with energy versus modulus of momentum transfer. And you can see that at relatively low Q, there's a very well-defined gapped excitation at something like 11 or 12 millielectron volts that's present at 7 Kelvin. And then as you head towards the phase transition at 30 Kelvin, the gap or the excitation softens and will eventually just collapse into the elastic line. So what's shown on the right are just cuts of the data that's shown on the left. So you can see the spin gap in this case, which is something like 10 MeV. The excitation itself has a bandwidth of about 6 MeV, and there's phonons and such that are above that. But you can see the part of the excitation spectrum that's temperature dependent on this temperature scale is the one that's at about 10 or 11 MeV. So this the way I've plotted this inelastic scattering on the right here is on a linear scale, and I've chosen a very low intensity scale so that I can see the relatively weak inelastic scattering, and so I lose information on the much stronger elastic scattering that's in this red bar at the bottom, but we can actually look at that as well. And so this is just the same data on the left and on the right, and the only difference is that on the right, the data is plotted on a log intensity scale. So now I'm not paying very much attention to the inelastic scattering. I'm looking at the much stronger elastic scattering. And what I want you to notice here are sort of two things. So one of these might be hard to fully appreciate, but there's essentially no difference in the Bragg scattering at 7 Kelvin and 50 Kelvin. And that's because the structure isn't changing as you go from 7 Kelvin to 50 Kelvin or vice versa. And secondly, there's a very nice relatively free region of momentum space between 0 and about 1.2 inverse angstroms, where there are no Bragg peaks due to the chemical order, if you like. And so this is a very good region to look for the possibility of very weak, dipole magnetic order, because there's no competing, nuclear Bragg order, if you like. So just by observation, you would conclude that there's no obvious signs of magnetic dipole order in this system, below these thermodynamic transitions that are somewhere between 30 Kelvin and 50 Kelvin. But we can actually do better than that. We can go to the world's best powder neutron diffractometer at the Institut Laue-Langevin and look at this more carefully and try to model different magnetic structures and see what we would have seen, if there were magnetic Bragg peaks present that corresponded to some of these structures, and that's what's shown here. And so we can model the expectations for simple magnetic structures like those single K and double K magnetic structures. And we can see, what we would have seen in this temperature subtracted data. So this data is 10 Kelvin minus 50 Kelvin, for example. And you can see that, had there been an ordered dipole moment of 0.06 Bohr magnetons, we would have seen it in this experiment. Anyway, the net result of all that is that there are no magnetic Bragg peaks present, and so our conclusion is that despite the fact that we can see these internal magnetic fields with μSR, and we can see this inelastic feature with inelastic neutron scattering, there's no magnetic dipole order present at T star. Okay, and then this is just showing for one of these systems, how well cubic symmetry is preserved down to low temperatures, and you'll see why that's important in just a minute or two. Again, we can look for very weak splittings of some of the cubic Bragg peaks, which would occur if there was some sort of symmetry lowering. And our conclusion here, actually, again, for all three of these materials, is that any potential distortion for symmetry lower than cubic would have to be below the 0.1% level. So basically, we don't see any evidence for symmetry below cubic at any temperature in these systems. So that left us with a quandary, and for a while it was exactly that. We kind of didn't really know what to do with the data. But then we got together with Aaron Paramakanti, who's sort of a neighbor at Toronto, and he really came up with this scheme, which the first part of the scheme is completely consistent with what I've already told you. You have this J equals 2 degree of freedom from the two d electrons, and that will give you a 5-fold degeneracy. So it's actually, once you've got J equals 2, it's almost like you're going back to the beginning of the problem where you have, 5 degenerate orbitals before you apply any other perturbations. And so you can do that again with the most general form of such a crystal field perturbation for a J equals 2 system. It has this form here, where this O40 and O44 are these Stevens equivalent operators. So this is the most general symmetry allowed form of a perturbation in this environment. And if if VF is positive, then the splitting, and there's nothing that requires it to be positive, I should add. But if it is positive, then the splitting is such that you have non-Kramers doublet and then some sort of a magnetic triplet. And of course, the gap between the two can be adjusted, and it can be adjusted to a scale that would give you the inelastic excitation that connects the ground state doublet to the excited state triplet. So you can set this to be about 20 MeV.
Bruce, you are a little over 25 minutes.
Okay, thank you. Good. Right. And so with that perturbation, you can work out the wave functions associated with these three states. And you end up with this non-Kramers doublet. And so in a pseudospin a half representation, this the one component, which is usually the Y component of the pseudospin operator, has an octupolar form. The other two components, the X and the Z component, have quadrupolar forms. Nonetheless, if you're in a J equals 2 MJ basis, then these are the wave functions, and you can work out that all the matrix elements of all the components of J within the ground state are 0, so you really wouldn't observe any magnetic neutron scattering. But there are non-zero matrix elements that connect J plus and J minus, connect them from the ground state doublet to the excited state triplet. So this would account for the inelastic scattering without the elastic scattering. Okay. And then the rest of this picture basically assumes that it's the octupoles that are ordering, right? You have both octupoles and quadrupoles present, but it's the octupoles that are ordering. And the fact that the octupoles are ordering means that you do expect some time reversal symmetry breaking, so you can expect some relatively low magnetic field that the muon would detect once the octupoles on the osmium start to order. And actually, if you place the muon at an oxygen site and you ask, what magnetic field would it sense, our sort of best estimate was that would be around 30 Gauss. And the estimate from the analysis of the MuSR data is 60 Gauss. So they're off by a factor of 2, but they're in the same ballpark. So actually, an octupolar ordered state would provide an explanation for all 5 of these observations, which were otherwise quite puzzling. So you recover R log 2 in entropy to high temperatures. You've got some sort of gapped inelastic magnetic spectrum that you can observe with neutrons, but there's no magnetic Bragg peaks. Also, if it's octupolar ordered as opposed to quadrupolar ordered, it would maintain cubic symmetry to low temperatures, which is what we observe. And octupoles do break time reversal symmetry, so that is consistent with the MuSR measurement as well. Actually, there's a very nice theory paper by Kalulian and Hae-Young Key and students that was published about a year or so later, which took the opposite point of view, that it's the quadrupoles that are actually ordering. It's serious work, and that's why I'm mentioning it here. But I don't find it as compelling as the octupolar case, because it requires that there is some cubic symmetry breaking. It just occurs at a lower threshold than what could be measured, which is certainly possible. but the magnetic fields that the MgOsR would measure would have to be a consequence of defects. They wouldn't actually be present in the bulk, but they could be present at domain boundaries, for example. Anyway, it's not a completely solved problem, although Leonid might tell you something else. So I don't want to preclude his conclusions. So then the last system that I'll want to talk about, and this is a system which we actually haven't done very much work on, but our most recent work is on this. So I'm going to tell you a little bit about this, and this is unpublished. And it's the 5D1 system, where you have a single electron, of course, in the quartet of states, and that gives you a J = 3/2 degree of freedom, which of course is fourfold degenerate. And the systems that have been probably the most interest here are this particular system, this barium to magnesium rhenium oxide. So it's rhenium instead of osmium, and that's why you get 5D1. And we've also, I'll show you a little bit of data on a zinc based version of this material, so barium zinc rhenate. And at any rate, just focusing on this middle panel for the time being, this is data taken from this paper from 2020. You can actually see in the thermodynamics that there's good evidence for two transitions. So one of which is identified as a quadrupolar ordering transition. So there's a structural transition here. It goes from cubic to some lower symmetry structure at about 33, 34 Kelvin. And then a sharper transition, which is associated with dipole magnetic ordering. And as you've got the heat capacity, you can recover the entropy, and actually the entropy that you recover is about R log 4. So it is what you expect for a single electron in this quartet of states. And then at low temperatures, you measure this net magnetization, which is somewhere around 0.3 or 0.4 Bohr magnetons per rhenium atom at low temperature. And I should just mention that this work was done on single crystals, very small single crystals. So it wasn't possible to do neutron diffraction on them, but it was possible to do resonant X-ray scattering on them. So that was done, and they can see a resonant X-ray signal that comes up at about 17 or 18 Kelvin. And they don't have very much data to work with, but the magnetic structure that they refined is a very unusual magnetic structure, but it's shown here. And it's, of course, it's a magnetic structure that has to have a net moment because they see a net moment at low temperatures. So that was one of their constraints. And this is in a tetragonal crystal structure, not a cubic crystal structure. In the layers along the C direction, you've got these ferromagnetic sheets of rhenium 6+ ions. And then they rotate from one sheet to the next by about 90 degrees, but they don't rotate all the way around. So that they have, they're almost perpendicular to each other and with a net moment associated with each other. So it's a very unusual magnetic structure. In fact, I can't think of another one that's like it. And it's not actually based on that much information. So anyway, that was our entry point. Well, this was our entry point, I guess. So this is, the phase diagram that the authors of this paper felt they were working with. So it's temperature versus, some measure of the strength of the quadrupole interaction parameter. And they felt they were in this regime where it's relatively strong. So you first get quadrupolar ordering and then dipole ordering. Whereas if it was weaker, you would go into something that's much closer to what we had in the D3 systems, where you've got some combination of a dipole and octopoles present. At any rate, these are the sorts of pictures that they come up with for the nature of the quadrupolar ordering. And I've already shown you this picture for the nature of the dipole ordering. And, so we've basically reproduced essentially all their results. We also see two features in the heat capacity. We can see the lowering of symmetry below cubic as we go down below about 33 or 34 Kelvin. You can see these cubic Bragg peaks, split into two. And, we've measured this on two different samples, barium magnesium renate and barium zinc renate. So all of this is very consistent with the original data. We also measure a net magnetization at very low temperatures. It's bigger. Actually, there's a typo here. It's bigger in the magnesium renate than it is in the zinc renate. But there's a net magnetization that's of order 0.3 Bohr magnetons per rhenium ion. But then when we go to do the neutron powder diffraction measurement, actually, if we take their structural refinement at face value and do the same sorts of experiments that we've been doing before, which is just looking at the difference between the powder diffraction at low temperatures and high temperatures, we can't reproduce the Bragg peaks associated with this structure. Okay, that would be given by what's shown at the bottom right-hand panel here. So this is the subtraction of two data sets, one at low temperatures, one at high temperatures. So if there were new magnetic Bragg peaks appearing, below 17 Kelvin, you would see them as big positive peaks in this kind of subtracted data. And actually, for exactly this structure, the Bragg peaks would be or the two biggest Bragg peaks would be at these locations here. And you can see that for an ordered moment of 0.4 Bohr magnetons, we would see this very easily. So our conclusion is that not only do we not see the magnetic Bragg signatures associated with this structure in our powder samples, but we don't see any magnetic Bragg peaks associated with, there's no signal that we can observe above background in our, so again, there's no obvious signal for dipolar magnetic order in the powders, although there is clearly a phase transition at 19 Kelvin. So this work is unpublished, and I'm afraid this is where I'm going to have to leave it for a variety of reasons. If for no other reason, I have nothing else to add to this story at the moment. I just wanted to leave you with an open issue. And so just in case you thought that everything was solved, let me assure you that it isn't. And then I'll just conclude by acknowledging my three students, student and postdoc, and Aaron, who really did pretty much all the work on the theory side that I was discussing with you, and his student, Srikar. And then these are the 5 or so papers that are relevant to this work. And so I hope I haven't run too long over time, and thank you for your attention.
Thank you very much, Bruce. Great talk. So I think there is time for some questions. Olivier, do you see anybody raising their hand?
I don't see anyone yet. So
maybe
people,
in the interest of time, Henri, I think.
Yeah. Hello, Bruce.
Oh, hi, Henri. Yeah.
I was wondering whether this transition could be seen by some NMR measurement. Of course, I assume Edwin has been involved. Right. Did you think about whether there is anything that can show up in I would
yes. So in fact, we are collaborating with Edwin, and he and a student they have NMR measurements or NQR measurements actually in the case of the 5D1 systems that are associated, I think with the barium nucleus, but we haven't gotten to the point where that's something that I can probably talk about in 6 months or a year, so more like that.
If there is no if there is no spin ordering, one could see something.
Right. Yeah, and so that's exactly the sort of thing that we were looking for. We are somewhat limited in the sense that we've only ever managed to synthesize polycrystal material. We've never come up with a single crystal. And of course we are trying to come up with single crystals, but our standard crystal growth techniques, which are floating zone techniques, haven't been successful. People have had limited success with flux growth, and so we could try some of those as well, but that limits the sorts of experiments that you can do.
Well, NQR could give something. I don't know what are the magnitudes, whether things are seen. You could
Right.
on
Yeah.
powders, you could find things.
Right. Yeah. That's
need single crystal, but
right. Yeah. So that's why we're approaching this, and so Edwin is leading that, and
I'll discuss with him.
Yeah, sure. Right.
Okay, Antoine.
If there's no other question, I'd be happy to ask the following thing. So you mentioned both that octupolar order is consistent and even explains the fact that the system remains cubic, in
Right.
contrast to quadrupolar. I'm not
Yeah.
totally sure I am aware of that. Can you, and I understand it, so can you explain?
Yes, it's just that the quadrupolar charge distribution is just typically not consistent with the local cubic symmetry, and so you would expect what usually happens, and what definitely happens in the case of the 5D1 system is that you get a distortion to some symmetry that's lower than cubic.
But here we are talking about, sorry to interrupt, here we are talking about sort of an interplay between the magnetic structure and the structure, right? So I guess
that's true.
It depends on magnetoelastic couplings, no? It's
Yeah,
not just...
Yeah. Right. And there, well, at least resonant X-ray scattering is seeing some sort of signal which the powder neutron diffraction is not seeing. So from the point of view of our measurements, we're seeing a finite magnetization at low temperatures, but we're not seeing any magnetic Bragg peaks in the sample, which is an open question as to why that is. But you're right, in the 5D2 cases, there's no obvious dipole moments there. And as I was mentioning, the components of the pseudo-spin-a-half operator, two of them are quadrupolar and one of them is octupolar. So it's natural to think that you could have a quadrupolar ordered ground state, which would also have no magnetic Bragg peaks. But those would normally not be associated with any time reversal symmetry breaking. And the quadrupoles, I sort of think of them as cigar-like things. And so if you try to order them up, they won't maintain the cubic symmetry. So but the argument that's made actually by let me just try to find it here. Yeah, this paper at the bottom, the argument that's made there is not that cubic symmetry is maintained despite the quadrupolar order. It's that it's actually broken, but it's broken below our tolerance. Yeah. So I mean, if you it's definitely a plausible argument, but I don't find it as compelling as the octupolar argument.
Okay, thank you.
Okay, I think we don't have any more time actually for questions.
Okay, very good. So thank you again, Bruce.